So on with the news. First item up we have here is scientists have spotted their first electron capture supernova. There's all kinds of supernovas, and we're going to be doing a presentation in the not too distant future. I've already started working on it regarding the various types of stellar explosions, novas, supernovas, hypernovas, unnovas, or false supernovas. So electron capture is different in that it basically is absorbing electrons versus protons. So you have electron capture and you have slow and fast proton capture novas. So this is apparently the first of a predicted but not yet detected type of nova. They've detected the first black hole swallowing a neutron star. How did you see that? So they have this lovely artist rendering here of what looks like a neutron star being sucked into a black hole. How dramatic. That's not real. So when you scroll down, you find out, how did they detect that? Oh, gravitational waves, like we talked about last week. So despite all of these lovely artistic renderings of black holes swallowing neutron stars that just fit inside the black hole, to neutron stars that are being shredded and sucked up by the accretion disk of the black hole. Like, no, all they detected was a little ripple in a gravitational wave and said, that must have been a neutron star being swallowed by a black hole. But the other aspect of it is, how far away was this? They didn't tell us how far away it is, which usually means it's pretty far away, because the gravitational waves we've found so far are typically not within a few dozen light years. Go away. And I have an article here from Nature. That's why the ads keep popping up, because it's directly out of Nature. They found a white dwarf about the size of the moon, but apparently it is much higher density, has a higher gravity field than would be expected of a white dwarf the size of the moon. So it's an oddball white dwarf. Once again, every time we observe, we're hopefully going to see things that are new and different, as opposed to same old, same old. And in this case, we saw a white dwarf that is denser than it should be. And it may be due to the fact that it's rapidly spinning, but we don't know yet. But it's an oddball white dwarf. A few years back, it wasn't recognized that the Milky Way actually had a central bar. Spiral galaxies can be barred spirals or non-barred spirals. Apparently, the Milky Way is a barred spiral. That just means it has that crossbar in the center, across the center. And now they're trying to understand, how did we get our central bar? Must have been dark matter. Well, it looks like, from what I read, there's kind of some that believe that and some that don't believe that. It says, well, the dark matter sort of corralled the additional stars towards the center and it elongated out the bar. And that's how you get a bar on your spiral galaxy. And the others are going like, that's a good postulation, and it's good thought, but where's your evidence? How do you say that's actually what happened? So the verdict is still out, as they say, but it's something to think about. This one I found a little fascinating. The planet Mercury has a relatively large iron core compared to other terrestrial planets like Venus and the Earth. It has a very much thinner crust and a very much bigger solid iron core. And what they're postulating is that it's because of the sun. So during the forming of our solar system, when there was a lot of dust and debris out there, anything that could be magnetically attracted was attracted to the magnetic field swirling around the sun. If you've ever seen sunspots, solar flares, things like that, those are all events on the sun that are driven by the very strong magnetic fields of the sun. Plasma generated fields from the plasma of the fusion furnace that is the sun. So if the sun has such strong magnetism, anything close to the sun, in other words, closer than Venus, would likely be drawn towards the sun. But then you had this newly forming planet called Mercury, and it got in the way. So a lot of the iron that should have fallen into the sun didn't, wound up being in the core of Mercury. And as the planet cooled, all of that high density iron sank towards the molten core. And then when the core finally solidified, you have a much larger iron core than expected. Of course, that's all just postulation. We know that the sun has a very strong magnetic field. And Hubble is still in trouble. They fired up, as I mentioned last week, they fired up the backup computer, but it had a similar problem to the primary computer. A spacecraft like Hubble has a lot of redundancy on it. And they also have a lot of modularization of components. So the computer is the computer, but then it's got memory boards. And you can switch between them. So if the backup computer's memory board is operational, but the primary computer isn't, then they can reroute things, hopefully, and have the backup computer run on the, let me switch it the other way around, have the primary computer run on the backup computer's memory. Because it's always better to run with the computer you know versus the computer you don't know. And the backup computer basically has been off since Hubble was orbiting. And I guess it's a record. Nobody claimed it to be a record, but from my knowledge, I think it's a record. There was a Falcon 9 SpaceX launch, and it sent 88 satellites into orbit. It was called a ride share. It's where a single Falcon 9 launch is sublet to multiple companies wanting to put satellites in orbit and just can't afford their own independent launch vehicle. So the Transporter 2 mission, as they called it, launched 88 satellites. Now, some of the satellites weren't independent. They were carrier satellites. So you'd see one sort of long brick-shaped thing ejecting from the top of the Falcon 9, and it would carry maybe half a dozen satellites. So one launch equaled 6. So, it wasn't all like 88 things suddenly sprouting out from the rocket. And then just to, say that, oh, since we had somebody else pay for the ride, we can share it. They launched 2 Starlink satellites as the last 2 satellites to be launched from the rocket. I just think that was showing off, but that's just me. They rolled the Super Heavy rocket out to the launch pad in Boca Chica, Texas. This particular one will only be test fired. It won't actually fly, but the next one will, supposedly. So they rolled it out, and they're probably going to be firing the engines just to make sure. How many engines have they got? Supposedly 36 engines, but we'll see how many engines it actually has. Ultimately, the Super Heavy is supposed to have 36 engines in it. They're not the Falcon engines. They're the, I've forgotten the name of them. Maybe you'll tell me here.
They say when it's going to test fire?
It's going to test fire soon, but it's not going up. It's just going to, static test its engines. The
Right.
actual launch will take place probably in the next month or 2. but that won't be this one. That'll be the next one. They've already found things they want to change.
Huh. No date though on just the static test fire?
They just say soon. I mean, they don't need a clear
Okay.
weather forecast for it because they're not launching it. They just need to make sure everything's right. And they've been having some problem with the local authorities and the FAA regarding closing down a particular highway going out to residential property on Boca Chica.
And environmental folks too.
Well,
Yeah, stuff's been raining down in protected marsh areas. Yeah,
okay.
they're
Well,
not thrilled.
the stuff that would be raining down is the burnt kerosene from the fuel.
And explodey parts too.
That's when it explodes. Yes.
Yes.
Well, you try your best for it not to do that.
Yeah.
Now, if it doesn't explode, should they accept it? I mean, is it dangerous to the environment? That's what they're protesting.
I don't think it's any more dangerous than what they launched from Cape Kennedy.
Yeah.
I mean, the only fuel safe rockets are the ones that use liquid hydrogen and liquid oxygen because the result of their combustion is water vapor and heat. So if you're mixing liquid oxygen with compressed kerosene, which is their RP-1 rocket fuel, which not just SpaceX, but all these commercial launchers are using liquid kerosene. The next thing they plan on looking at once they want to take this thing up to like Mars is liquid methane, compressed methane. But how completely it will combust, I don't know. But it would be cleaner than kerosene. Think of it this way. Kerosene's the stuff you get at the bottom of the tank after you've already taken all of the natural gas and the gasoline and even the diesel out. Kerosene's the sludge at the bottom. And Russia actually docked a cargo ship at the International Space Station. That's not so much news, that, you know, because they've done it on occasion, but it's not manned. There's no crew on board. The cargo ship, not the ISS. They complained that on its way from launch to the ISS, it had a chance of encountering space debris or Starlink satellites. It encountered neither one of them. So you'd have to ask, well, why did you think that was a problem when it turned out to actually not be a problem? So I would want to find out how much money Russia got to say it's going to be a problem when it wasn't a problem. Okay, how many people know of Wally Funk? You can hear the fireworks in the background. That's just the neighbors. They went and spent money, now they want to blow it up. Back when there was a Mercury 7, which was 7 white male astronauts, there were actually 6 female astronauts that were in a separate clandestine program. That made the Mercury 13. Wally Funk is now, I think she's in her 80s. She will actually be flying with Jeff Bezos on the New Shepard launch vehicle, which, you know, it's about damn time, as the saying goes. But I'm sure she's getting a piece of the action for the public notoriety. I'm just happy to see that, you know, we're recognizing historically that things that were kept a secret, and they were kept a secret up until recently, have finally been shown to be not how we should treat people.
And she'll be the oldest person to go into space too, right?
I don't know how old John Glenn was.
I think I heard a news report that she will be the oldest.
Okay. Well, she's not actually going into orbit. She's only going into suborbital flight because the Blue Origin rockets, the new Shepard model, doesn't actually go into orbit. It just goes up and down. The New Glenn rocket that someday they'll build, someday Blue Origin will build, will actually be their first orbital rocket. But like I said, I'm just pleased that we're finally admitting the prior error of our ways, trying to do something to recognize it, but it is private. It's not the US, it's not NASA or the government that's doing this. It's a private concern. It's, Blue Origin, Jeff Bezos with his billions, but more power. And as you can see, in 7 days, 11 hours, 18 minutes, and 30 seconds, Virgin Galactic will launch another suborbital flight with their spacecraft. Branson's actually going to go up on board this one, and the billionaire to billionaire bragging rights is going to be Branson will go into orbit before Bezos.
Yeah.
But neither one of them is going into orbit. They're just going up and then down. So they're not doing anything more than Alan Shepard initially did. But if you have the right amount of money, you can fly with us. I had to include something. This was from a day ago, so I had to update my presentation on quantum computers to take, be aware of this. Some people might be aware of something called SoC technology, system on a chip. They're going to start looking at doing that for quantum computer processors. And the reason is you can't have them so close together. The qubits, you can't have them so close together as to make a high density integrated circuit because they'll interfere with one another. So how do you get things that need some, millimeter separation into a small space? And you use this system on a chip. You create a little wafer of silicon, and then you place the component on it, and then you run little tiny microscopic gold wires between them. So that's what they're saying here, is they're going to use SoC technology. There's a company, Rigetti, is it? Yeah, Rigetti Computing. I guess they're out of Italy. That plans on building this. The funny thing is that they're going to take it from 16 qubits per computer to a whopping 80. And if a qubit is equivalent to a bit, and you have things like megabits and gigabits, quantum's not there yet because they're not even breaking 100. But we'll get into that during the presentation. We have these machine learning systems. You feed algorithms into them, and they can very quickly crunch on them. They're not quantum computer speed, but they have a lot of parallelism in them, like supercomputers. So they can process a lot of data very quickly. If they don't have to work through data. They can be given data and just crunch on it and then interact with one another. And so that's, learning computers. And learning computers are not the same as quantum computers, but in this particular instance, they're actually putting quantum physics experiments into learning computers and having them decide what experiments to actually run. And what they found out was the learning computer figured out there are quantum physics experiments we haven't thought of running yet. So they're suggesting what new things we can try. If you've ever seen any of those science fiction movies where the computers start to get smarter and smarter somehow all on their own, they come up with new science and new math, and
then they go by themselves.
yes,
And take over the world.
yes.
Colossus, the Forbin Project.
Oh, one of my favorite movies, yes.
I just saw the Tomorrow War. What an interesting sci-fi that was, where they go back in time and grab people to fight the aliens that are taking over the world.
They're always taking over the world.
I know.
Yes, I did. I actually did watch the Tomorrow War, and
Yeah.
I mean, it's got some science that doesn't work right, but let me just say it was entertaining.
Yep.
I wanted to see the lead actor Chris Pratt doing something other than Guardians of the Galaxy, so
Yeah. Or
I wanted to see what
Jurassic
his skill
Park.
set was. It did have a nice hook at the very end. That was
Yeah.
pretty good.
Climate change.
It's on Amazon, so if you have Amazon Prime, it doesn't cost anything to watch it. But I found that, well, if you can travel in time, why don't you just go back and stop the aliens when they first land? And they had a really convenient reason for that. Well, we can only go back so far, and we're already missed that window. Oh, how
Yeah.
convenient. That's the kind of thing that if you watch Deadpool movies, he would just stare into the camera and go, lazy writing.
Well, didn't they actually do that where they went back and tracked to where they originally came from with the climate change and stuff?
Yes, but it was only because they ignored the military government leader who said, I'm not going to spend money on that.
Right.
And then as soon as they found the aliens and destroyed them, it was his great idea to do it.
Oh yeah,
Yeah.
He must be a Republican.
I don't know.
Yeah, I was thinking that.
I don't know.
Credit for all the good laws.
Yeah.
Even though they voted against them.
Yeah. Some things in addition to the news. I posted the LIGO session from last week on YouTube. I sent an email off to, he just likes to be referred to as Atta, who is a physics department head at FAU. I'm an FAU alumnus. Go Owls. So I sent an email off to him. I was on the PBS Stargazers presentation as a, just somebody commenting in the audience as Broward Astronomy. And so I said, well, I'll send him a link to the YouTube page and he can, look at our videos and see if he enjoys them. I think he'll like the one on Cherenkov radiation, but maybe he'll like the one on LIGO as well. So we'll see what he says. So on July 22nd, Jill Tarter of SETI fame, she was the person, I guess you could say, that was the Jodie Foster character in the movie Contact, if you wanted to map them. So Jill's retired from SETI now. She's emeritus. So she'll be giving a presentation at the Astronomical Society of the Pacific Summer Session entitled A Cosmic Perspective, Searching for Aliens and Finding Ourselves. In the news that I sent around in the email, there's a hyperlink. So if anybody wants to watch that, I've already got it on my Outlook calendar and we'll join in, likely as Broward Astronomy if they're doing it using Zoom. So I might, pop in with a question or two for Jill, like, hey, Jill, why isn't SETI looking for ET using gravity waves instead of just light and radio? So as I mentioned earlier in an earlier session, in July, I'm scheduled for an interview with the Broward County Library's Creation Station folks. So I've got, I think it's on the 13th is the test rehearsal to make sure the technology is working. Not everybody knows how to use Zoom. So we'll do that. And then I think around the 23rd of July is when the session is actually recorded. When it's going to be posted on the Creation Station site, I don't know. For sometime in September, I haven't received further details yet. The James Webb Space Telescope Institute is going to host a community online session, which I'm either going to be a host or a panelist or something. They haven't sent me the details, but I guess it all depends upon if they make the decision, is James Webb going to be launched this year or next year? I'm going to guess that if it's going to be launched next year, they don't want to have such a forward-looking presentation. They want one shortly before it gets launched. So we'll see.
With you doing these outreaches, you know, it sounds like you're doing a couple at least there that you mentioned. You will generate popularity and people will want to hear you on other topics. Have you thought of opening up? Because I mean, this is a great
Yes.
time period to, okay.
Yes, I have. I'm trying to think of, I can open it for, I guess you could say, solicitation to join rather than just general public. So I could open it up as a solicitation. If you remember the old Yahoo groups, you couldn't just straightforward join. You had to request to join, and then a moderator would approve you to be joined. When you get to Google groups, they're more private, and you there's no button where you can solicit to join. But I can put on the YouTube site that you know, there's a link you can click to solicit to join, and then I would still have approval over accepting whoever I wanted to join, denying others. So I have to find the appropriate vehicle for doing this, but I do know that I want to expand this out to almost the general public, but I think they can request. You know, on the YouTube site, there is a place for comments. And if they say, how do I get on board with this? How do I join this? You know, I can see those comments and approve them or not, which would say, there's kind of already a vehicle for saying, I want to partake. But yeah, I think it needs to be more open.
That would be great. Thank you.
So tonight's presentation is on quantum computers. Next week's presentation is on commercial US spaceports. The following week, I'm starting to work up something on basically data sensing, how everything that we sense in all of our technologies is simply a matter of counting electrons. And I actually spoke with an MIT and Caltech PhD yesterday. He thought about it for a moment. He goes, yep, that's true. So everything we sense, when you dig down through, you find that it's simply a matter of counting electrons. Even gravity waves. Gravity waves, we indirectly count electrons by the interference pattern that gets detected when the gravity waves wiggle the laser beams. And we detect the changes in brightness of the laser beams, and that's basically the light creates electrons. We count the electrons.
I think the jury is still out on what an electron really is.
Well, quantum physics says when you go to sample something, it's not where it was, it's where it was when you sampled it. So, you know, what an electron is it a particle? Is it a wave? I think it's something that we're grasping at straws to find an analog for at this point. I think a lot of things in subatomic physics are like that. Is it a packet of something, or is it a wave of something? I've always thought if it's a wave, it better have a wavelength, because how long is it? It has no width. Sorry, it has no thickness, but it has width. And you have these duality experiments in physics where you shine a laser through two slits, and is it a wave or is it particles? It all depends upon the interference mechanisms that you're dealing with. So, you know, we're struggling with that. But I do think that from what I've read, everything that we electronically detect, sense, count, measure is all simply a matter of counting electrons. But we'll get to that in more detail in a couple of weeks. And just on a project before we get started with the presentation, if you saw the picture I showed last week of the astronomy remote control camera that I'm planning on mounting on my house. I ordered the aluminum tubing to do the wiring install, and one piece, I thought I had measured it correctly, and then when I actually did a double take on it, went, oh, that's not going to be long enough. I need to replace a 2-inch piece of aluminum tubing with a 10-inch piece. It needs to get above the roof before the camera's there. So that'll delay it like at least a week because they're not shipping because of the 4th of July. I ordered from a place out of Georgia, which I thought it was going to take a week. It only took 3 days to get to me. So, but I need to replace that one short section of aluminum fitting, and then I can take pictures of it and make diagrams of it and show it to the city of Fort Lauderdale and saying, it's an astronomy camera. I'm not going to be looking in neighbors' windows with it. Trust me, it's upside down.
You could.
I did find that OBS Studio, the little tool that you use for doing the Zoom sessions and such, it'll actually talk to that camera, and I've set up that camera as something the OBS Studio can tap into the Zoom session. So I've already got that part of it running. I just need to get it mounted outside where it can see something other than the walls in my kitchen.
I have a question.
Sure.
I'm thinking about what the question Joe asked about the electrons and it being out, like there isn't a firm definition right now of electrons.
Well, no. It's not that we don't have a firm definition of an electron. We've
Okay.
measured the size of an electron. We understand the charge of an electron, how much energy one electron holds. We
Okay.
understand the polarity. An electron is negative and a proton is positive. So
Okay.
we understand that. We understand the orbits of electrons around the nucleus, the core of an atom. So there's a lot we know about electrons, but as to physically what is an electron, we know as little about electrons as we do about protons and neutrons. They're
But the-
things. Now,
Okay. My point was, is how do you count it if you don't have a,
oh,
I mean, if it doesn't have a physical, then,
okay, there is an electron, there is a International Standards Organization,
okay,
SI, and they've arrived at a set of baseline standard values. One of the last presentations I did from Fox Observatory was on standards and the fact that a lot of the things that we base them on are arbitrary, or to calculate B, we use A, but A uses B, so it's circular. A lot of these standards are just, well, we've got to put a stake in the ground somewhere to measure this. And how do we measure the energy of an electron? Well, we use a unit called a coulomb, but a coulomb is a force that we measure. How do we measure the force? Well, the force is something measured as a change over time. Well, is an electrical force different than a physical like push force? They're related. They're both measured in Teslas, but we've come up with these arbitrary units for things. But what is the substance of a subatomic particle? That we don't know. But we do know things like how many quarks does it take to make a proton? How many quarks does it take to make an electron? We kind of know those because we've smashed apart protons and electrons. Protons and neutrons. We've smashed them apart so we know what their innards are like.
Yeah, the up quarks, the down quarks. Yeah.
Yes. And you have a triplet in both of them, but it's a different mix of triplets of quarks. And we come up with these funny things like up quarks and down quarks. And then the one that we, went off in weird directions, we just called a strange quark. So if you ever look at a chart of subatomic physics, you'll find that like when you dig down, it's about 95% of it seems to have some rational thought behind it. But that last 5% is, how come there's no number there? Well, if there was a number other than 0 there, it wouldn't work out right. But is there a number other than 0? Well, photons at rest have no mass. Well, what about photons when they're moving? Because we know from LIGO that if you smack a high intensity laser beam, which is a density of photons, against the glass mirror will rebound at the microscopic level. So that means that in order for it to do that, the photons had to have mass, they had to have momentum, and they transferred that to the mirror. So a photon at rest has no mass, but a photon that's moving should theoretically have mass. How did it do that? How does it go from not having mass to having mass? Well, when you charge up the electron and it changes its orbital position to an outer layer, and then it wants to get back down to the lower layer, it spits out a photon. So it somehow contributes mass to the photon. Yeah, you got to look at the quantum stuff with sure, that's what we know now. What are we going to know in the future? Maybe something different. We have to keep looking. Subatomic physics is always fun.
Where's the charm come in? I love that name, charm.
Yes, there is a chart that will show you the different types of quarks, and you have charmed quarks and you have strange quarks.
Okay, comes in with the strange.
Yeah. Okay, tonight's presentation is on quantum computers. To quote Spock, I just described them as fascinating. So some people might say this is another opinion piece. Yes, I will explain quantum computers, how they could relate to astronomy and space science by calculating things, but not yet. I'll explain quantum computer technology, and then some thoughts on a possible future for quantum computers in the realm of computing, since that's where my educational background is in computer systems. So, for those that remember the old days from the 1970s. So in the lower left here, we have an IBM 360 computer. We actually had one of those at Broward College. It was a 360/40, I think. They took up an entire room. I mean, not just a small room like a bedroom size. They took up like a living room, dining room size kind of computer. And that was one processor. Plus underneath the flooring was a couple of feet of space for just running massive amounts of very large diameter cabling. They didn't stay up all that long. You couldn't call them on, 24/7 by 365. They were slow. They executed a few thousand instructions per second. They had tiny amounts of memory, 512,000 bytes, not today's gigabytes. They used things like punch cards and reels of magnetic tape for their I/O. They were physically massive. They required special cooling, literally tonnage of AC. They required special power. I think they ran on 400 hertz power. I don't know why. I'm not an analog, double E, but they ran on 400 hertz and very high voltage. They were complicated to program. If you wanted it to execute faster, you wrote your programs in machine language. And they were very expensive. You didn't generally buy one because it would cost you over $1 million. You would lease one. And then at the end of the lease, you either paid even more or IBM came back and reclaimed their property. So to give you an idea of the comparison, in the lower right there, there's a picture. There's one of those little memory chips like you'd stuff into your cell phone. It's called a micro SD card. That has 8 gigabytes on it, 8 billion bytes. That's giga. So beneath the micro SD chip, you see all those little round things? Those are magnetic memory cores from
Core.
back in the day. And you can see that there were little copper wires that ran through them. And you had a read wire and a sense wire and a reset wire. So there was at least 3 wires going through every one of those cores. And if you count them up, you'll see that vertically there's 8 cores, and horizontally there's 8 cores. So it took 64 bits to make one group of 8 bytes. So here you have 8 bytes that is larger than today's 8 gigabyte micro SD card. And that's just since the 1970s. So quantum computers are currently all the rage. Everybody's saying that they're going to solve all the world's most complex problems and do it faster than these so-called classical computers. You know, those things you own nowadays, like laptops and such. However, when you scrape below the surface, you'll find that quantum computers are currently unreliable, error-prone computing technology, just like the earliest supercomputers were. So, you know, give them some time. They just need to solve a handful of issues, as all new technology does. And the difference is, will they be able to solve the problems they can solve? And what about the problems that are just the nature of quantum physics in general? How will they solve those? Well, we'll need new technology, and we might even need some new physics. So in the meantime, just give us billions more in research funding, and every few years we'll tell you we need another few years. This is not the first time that new technologies come along where the technology wanted to be more important than the computer that is using it. If you remember, there was once a thing called bubble memory. Little streams of magnetic bubbles would circulate inside of a chip, and it had a long latency because the bubbles ran in sequential order. So if you had millions of bubbles, you'd have to wait for the bubbles to circulate, and they circulated inside of a field, so they were constantly moving. So you had a latency, like, I want to get at this bubble, but I can't because it won't come around again for another 20 milliseconds. So it had that problem. The bubbles could get cold, so they needed a warm-up time. And of course, how big can you make them? Well, at some point it just got ludicrous. So bubble memory kind of went away. And today we have solid state disk drives that solve that problem because they're terabytes. At one time we thought we've got to make hard disks smaller and smaller. And we went from like 13-inch platters to 5.25-inch to 3.5-inch to 1-inch. IBM actually for a time made 1-inch rotating media hard drives. But the problem was, how physically small can you make it? And 1-inch was about it, because mechanical stuff, unless it gets to be quantum, you can only make it so small before it becomes unreliable. There were computers at one time, the Burroughs 2900 series, where every time you switched from one process to another in the computer, it could actually change instruction sets. So if you were running a Fortran program and you also wanted to run a COBOL program, you would have different instruction sets. So when the COBOL program wanted to run, the computer's instruction sets were optimized for running COBOL. And when the next process wanted to run and you switched, it would change the instruction set of the computer to be better at running Fortran programs. And that was just too inflexible, because there's a bunch of other programming languages that you're not going to constantly reinvent the instruction set for. So they just became too expensive. But for a time there was that. People may have heard of object-based computers or object-based programming. Intel made a processor called the 432 that was very expensive. They didn't get a lot of high quality yield out of it. So it was expensive chips because it was complex technology, as well as being not 100% reliable. So you had object-based computers, but the amount of processing they had to do for things like garbage collection and for relinking of objects, they were just too slow. And every time object computing technology wanted to make a change, you got to go back and redo some hardware. That's inflexible. So between it being inflexible and too expensive, they just gave up on trying to make object-based computers. And now we do all the object programming in software and just make the overall general purpose computer faster. So people have probably seen false starts on 3D holographic computer displays. This is where you can see a 3D display without special glasses or headsets. Sort of, if you watch the Marvel movies and you watch Tony Stark looking at things in 3D without any particular kind of projectors, that kind of stuff. But that's science fiction movie fantasy. We don't have those yet. Every time they try and come up with displays that are kind of 3D, scratch below the surface and you find out, well, they're not really 3D in open space. They're kind of a limited physical space, so you can't make large 3D displays. And even the 3D display capabilities of large televisions aren't selling too well, so most TV sets don't support the 3D glasses anymore. There are some that do. Most of the time to watch 3D, we just use the passive, the D2 color, the red, green, or red, blue glasses, or the active shutters where it flips the shutters back and forth on your eyes at a high enough rate that you don't notice. A lot of the 3D movies are like that. So anytime technology wants to stand out larger than the concept of computing itself, be careful, because it really should more appropriately be just a peripheral, an add-on, an addition to computing technology. It itself isn't computing technology. So when you go to the store, you don't buy a quad-core processor. You go to the store because you want to buy a laptop computer that just happens to have a quad-core processor. So it's about, putting things in perspective versus the hype of technology to get you to buy new. Windows 11 coming out with restrictions on, what kind of processor chip it supports will probably sell more laptops than any oddball new technology, because it's just constraining what will run it. You're already talking about having millions of what they call zombie computers that can't run Windows 11 that'll still be on Windows 10. So when Microsoft stops supporting Windows 10 in another 5 to 7 years, they'll be running a version of Windows that is no longer supported but would still work. However, in computing technology, when you solve the problems, they're success stories. So think of computer memory. When I first was encountering computer core memory, magnetic cores, the magnetic cores were as big around as your little finger. And the real-time computer I worked on actually had a 1K byte computer array that was like $16,000 because they were hand wound by people. They actually took what looked like darning needles and ran the wire in the cores and would attach the cores onto a little circuit board for 1024 hand wound cores. But we progressed the technology. We went to 1K socketed chips, and now we have these things that look like little sticks of gum that hold 64 gigabytes. So if technology solves its problems, you're going to find it puts more out there for less money per item. We have monochrome and color laser printers. Today, the toner that you put in the printer costs more than the printer. So a lot of times when you go, well, I see there's a sale, I could buy a new printer for $75, or I could buy a toner cartridge, which is just a toner cartridge, not the drum unit. I could buy a new toner cartridge for $65. I'll spend the $75 and buy a newer, faster computer that comes with a full toner cartridge. We have drop-on-demand color inkjet printers. The ink is too expensive. It's still too proprietary. And the capacity of ink per cartridge is limited. although you see commercials on TV for much more ink per cartridge, about 4 times the amount of ink, but it's still limited. So, there's not an infinite supply of ink, but you can sign up for a delivery program where, every few weeks it'll just ship you a new set of ink cartridges under the premise that you're going to consume them. Well, if you go on vacation and come back, you're now going to have, 2 weeks worth of ink cartridges that you haven't used. So stop sending me more. Solid state storage has progressed, but it's gotten denser and faster such that the disk drive interface that they used to use back when they were rotating media hard drives, where that interface was faster than the hard drive, is now the other way around. Solid state memory is much faster than that old disk interface, so they had to come up with a new one called PCIe NVMe. That's like 8 times faster and can do multiple channels simultaneously. That really makes the memory go faster. So if you're going looking for a new laptop that has solid state memory, solid state disk drive, it's not a disk anymore, it's solid state storage, check to see that it's not SATA 3, that it's PCIe NVMe. And you'll be thankful because the memory will be much faster, and it's a module that you can swap out when they make them higher density. If you remember, at one time, GPS receivers were these handheld things, and now they're just a component built into your mobile phone. So again, if the technology gets cheaper, higher density, better, it just kind of dissolves into the woodwork and just becomes a part of the computer. It's no longer a standout separate thing. Wireless communication, Wi-Fi. It used to be you'd go buy a Wi-Fi adapter for your computer, and then it became built in. Now it's just, well, it supports the 2.4 gigahertz, but not the 5 gigahertz. And now the latest computers are just, it supports 2.4 and 5. And now they're talking about, well, since we can do that in software, why don't we just throw in a 5G adapter into the computer? So your computer will support Bluetooth, GPS, 2 frequency bands of Wi-Fi, and 5G. And it's all in the same size laptop that just got thinner. Computer displays, they went from big tubes, CRTs, to LCDs, to LEDs, to organic LEDs, to quantum LEDs, and they went from 2K to 4K to 8K, and they went from 16 colors to 255 colors to 16 million colors, that's the 24-bit, and now there's something called HDR, high dynamic range, over 1 billion colors. Not that your eye can see all those colors, but. And cameras. Cameras used to be separate things. Even digital used to be separate things. Now they're so small that, the latest mobile phones actually has 3 cameras in it, because it's actually cheaper to put 3 cameras in it than it is to put the mechanical mechanism in 1 camera for zooming. Touchscreen displays. They're more accurate, higher resolution, and faster. They're just a given part of, tablet computers include them. Windows computers include them. But certain models of Apple computers, like Macs, typically don't have touchscreen displays. They just have a touch strip. Marketing. Computer size, capacity, performance, total cost of ownership has gone from mainframes to minis to desktops to laptops to handhelds to tablets to mobiles. As long as that progression keeps going, technology will keep advancing. So we're now looking at quantum computers that are big, but if they keep improving, they won't be big for long. There are other technologies that kind of get to a plateau and they're waiting for the next advancement in technology. 3D printers. I'm on my second 3D printer. This one's much better than the first one, but it's still got some foibles. Sometimes when I go to print something, calibration's off and it doesn't print right, as was known as a print fail. It literally just squirts plastic all over the tabletop, and it didn't print right. So they need to fix that. And what type of technology they're going to use? Plastic filaments, resin, metal sintering, and then how best do they do multiple materials or multiple colors? So it's a technology not there yet, but it's a kind of a plateaued technology. I think will get better in the future. They're just waiting on some new stuff to come out. Okay, classical computers. This is a little heavy, but trust me, once you understand this, you'll understand basically what a qubit versus a bit is all about. Dig deep inside of any computer, and you're going to find that it's based upon things called bits and logic units. A logic unit is the thing that does all of the underlying functions to make computers work. And strangely enough, things like add was once not a single instruction. You had to actually write software to do an add. When I was in high school back in the day, I actually wrote software that would do an add, an integer, fixed point, add. And it took running Xor gates and bit shifters to do an add. But at the core of it all is this little magical thing called an Xor gate. It's an exclusive OR gate, and it works off of ones and zeros. So if you have a 0 and a 0, that produces a 0 when it runs through the gate. 0 and 1, you get a 1. A 1 and a 0, you get a 1. A 1 and a 1 is special. It produces a 0, not a 1, but it sets another flag saying, and carry over to the next bit. So that's at the core of computers. Now that's just one bit. Computers have these little storage registers that might be, 64 bits, 128 bits, very wide, and each one of those requires bits. And if you have lots of those, it requires lots of bits just for the registers of the computer. Well, we now have enough of these transistors to make enough bits that we can just throw things at them. As in, we don't go to the trouble to write, hardware logic that does adds anymore. We actually just take all the possible values and generate fixed logic circuits of it. So when you want to go add two numbers together, it already knows the answer. It just goes data in, data out, does it in one instruction. So if you want to learn more about classical computers and their central processing units, here's two videos. They're not all that long, 18 minutes and 25 minutes, that Intel Marketing puts out to explain the central processing unit. But if you want to learn more about classical computers, that's the central processing unit. Okay, what's all this quantum stuff? Well, there's certain vocabulary that comes out of the world of subatomic or quantum physics that quantum computers does base itself on. The quantum state. You need, like a computer has a bit that can go a 1 or a 0, you need something at the quantum state, the subatomic state, that you can count of as being this way or that way. And there's two things they've come up with. One is electrons. The spin of electrons. Are they spinning this way? Or are they upside down and spinning that way? So that's the spin of an electron. Photons, the phase. Is the phase of the photon this way or the phase of the photon that way? In LIGO, last week we learned a little bit about when the laser beam goes through the beam splitter, it makes one of the beams 180 degrees out of phase, and that gives you your interference pattern. Well, photons can be flipped in their phase, but it turns out the preference is quantum computers are typically based upon electron spin, not photons. And we'll get into why that is. But how you position the electron spin is called its superposition. Superpositions aren't necessarily just a 1 or a 0. They can be probabilistic. They can be any place in between. So they like to say that the superposition of a qubit is a value between 0 and 1, not just 0 or 1. So this stored computing state, the superposition of electron spin, is called a qubit. Sometimes you'll see it written as QBIT, but predominantly it's qubit. How do you link these things together? If I want to link 2 bits together to make something like an adder, then we use quantum entanglement. So I have 2 electrons and I associate them. So when I flip one, it flips the other. But the problem is it flips in the same way. And if you look at the adder, that Xor gate, when the Xor gate saw a 1 and a 1, it made it a 0 and it carried a 1. So something for them to figure out. But here's the Achilles heel. It's something called decoherence. These electrons that they've set the spin on are very susceptible to influences. Temperature changes, remember, temperature is nothing more than energy. Magnetic fields, which is nothing more than energy. And vibration, which when you get down to it is another form of oscillation of energy. These energy influences on the electron tends to destabilize it. So if you think you've got the electron spinning one way, all you need is a little temperature fluctuation, a magnetic field, or a little bit of jarring of the computer, and it could go the other way. It may not affect it at all, but it might flip it. So that makes the individual qubits unreliable. So what do they do to solve this problem? If you remember back to the long range deep space communication, you use extra bits to do the quality calculation of the data to detect when you have an error, and you use extra bits to correct for the error. So they're taking extra qubits to do the error detection and correction for when a qubit suddenly goes wrong. So decoherence is the current Achilles heel for quantum computers. All right, here's a comparison between, on the left, you see a gate, a pair of gates here. You have an XOR and you have an OR gate, and that produces your basically 1-bit computer. And then the circle up there at the top is a qubit. A qubit can be definitely a 0, definitely a 1, or it could be maybe a 0 or a 1, probabilistically. And of course, since they're not gates, they have to have their own diagram for what is a qubit. So you can see over here on the left, here's my inputs, A and B. Here's my inputs, Q0 and Q1 for qubit 1 and qubit 0. Here's how I interconnect the two. And here's how I interconnect my qubits. And then here's my outputs. And here's my outputs. So you've got to have different diagrams for basically saying the same thing. On the left is 1 bit. On the right is 1 qubit. So this week there was an IBM Research Center announcement where they tried to prove the value of quantum computing over classical computers and their bits. And they decided to use the concept of scratch storage locations. In other words, if you're computing something and you need to temporarily hold on to some data, it goes into scratch storage, which you reuse for the next calculation you're doing. So they had to prove that a bit can only hold 2 states, 0 and 1, kind of obvious. And then a qubit can probabilistically state change anywhere from 0 to 1. So they wanted to prove this range of values versus just 2 values. The second thing that they set to prove was a bit has a limited number of Boolean functions that it can do. It can do ands and ors and nots and XORs and things like that. But since a qubit can take on all these different values, it can have a whole lot more functions that it can do. And there's the link to the IBM research paper. I'll include that in the notes. So the benefit of storing more than 1 state in a single location is, it can store more things. That seems reasonable, but not if the thing you're storing can't be deterministic. Is it a 1 or is it a 0? If it's somewhere in between, I got to process it as both. So it adds to the complexity, even though it can process it very fast. And having a broader set of Boolean functions might not be usable if you can't find a practical purpose for them. If I encode 4 states in 4 bits, that actually holds 16 states, 12 of which I might not be using. So it's sure it can do more, but what am I doing with the more? But the crux of their research was, in order to make the answer come out correctly, and I'm often fond of finding these, if you want the answer to be what you want the answer to be, change the test. And they did. They constrained the capabilities of a classical computer bit to make it look more like a qubit. And they essentially handpicked a single qubit that's perfect, that doesn't have any reliability issues, which doesn't exist in any quantum computer products. So while the research is theoretically meaningful, it's unrealistic that you can actually create a product that would do that. And most likely it's just a promotional stunt to get people more interested in quantum computing. So what can you do with so few qubits? Turns out there's a whole branch of mathematics called linear algebra. It's all that stuff that unless you were into math, you were like, oh, that's hard. It's hard to comprehend. It's hard to actually work it out because it takes so much.
You could take a course on it for free with
Yes.
Khan Academy.
Yes, but if you do take the course on it, let me know if you enjoy tensors and Hamiltonians.
Well, I like vector analysis. Yeah.
It's just math. It's a process. If you
Yeah.
explain the process and understand it, you can make use of it. And trust me, linear algebra has its uses. But they found out that since all you need is a few bits and you can reflow the algorithms within the qubits, it makes them usable for doing linear algebra, which is great. This will be some of the earliest useful purposes of limited quantity qubit quantum computers. The problem is it's like the early supercomputers that didn't run real programming software. Unless whatever you want to accomplish algorithmically maps well to linear algebra, you're not going to find that a small number of qubits quantum computer is going to be usable by you. You might say, well, let me know once you get a few megabits of these qubits, because I can't do anything with 64 of them. The second thing is if your classical computer problem is what you're trying to solve, a quantum computer won't be able to run it. Because if you want to run something like, I don't know, sorting a long string of characters, which is something computers do a lot of, you're running sequential algorithms where having, more things running parallel doesn't really help you any. It's just a serial problem. Okay, so I've already described deep down that classical computers have these things called Boolean bits, and qubits are these things that quantum computers have. And as long as you only have a handful of them and you're required to run them in liquid helium, you're not going to make a lot of big quantum computers anytime soon. Okay, this I found interesting. Since quantum computers are cooled in liquid helium, any excess heat might disturb those very sensitive qubits. How can you get extra heat? Well, anytime a computer takes a value that's a 1 and changes it to a 0, the energy that was making it a 1 has to go somewhere. And until I actually read up on these on quantum computers and the concern for them, I never thought about this. I always just went, okay, that 1 bit became a 0 bit. I didn't think much of it. The 1 just kind of went away. No, the 1 is energy that has to go somewhere. And there's these special kind of gates that can redirect the energy to where they can make another 1 elsewhere. They're called Toffoli gates. And, we don't worry about that in classical computers because they produce heat. And we found other ways to making them produce less heat. Change the chemistry of the chips and such, and put in power distribution system to spread out the power. But we don't think about it this way. But much like you'll soon find in another slide where we talk about the difference between a CISC computer, CISC, and a RISC computer, RISC, you're going to have eventually this concept of, I can't make a classical computer produce any less heat because it doesn't pay attention to Toffoli gates. So as soon as classical computers start being based upon Toffoli gates, they're going to find that that 1 bit becoming a 0 bit has a way of distributing the heat as energy to other circuits. So deep down, that means that even though you might still be using a classical computer, it can use some of the concepts of quantum computing to improve classical computers. Okay, a picture. This is one of the Google quantum computers. This is not the entire computer. This is the central part of the computer. And if you see all those little white stringy things with the curly cues, like little pigtails, each one of those little white strings goes to 1 qubit. And there's 2 of those that go to each qubit. So think about how small can an individual qubit be if these very small but still sizable little coax cables have to have 2 of them going to every qubit. And then when you want to join all those coax cables up so that you can process the data, you see down at the bottom all the little terminal strips where the coax cables go in, because you've got to get those radio frequency coax cables to something that can emit the microwaves. And then when the microwaves come back, you've got to get something that can detect that the microwave says it's a 1 or a 0. You can see the size of this thing because there's 2 guys standing in the background. Now, these large gold discs that you see, that's the inner framework of the quantum computer. The thing you see up at the top, the very large coppery looking braided things, that's power distribution. So quantum computers take in a lot of power to run all the microwave circuitry, and they produce a lot of heat, but the chamber that actually encloses the quantum computer covers all the way out to the edge of those gold discs, and it's just a giant, you know, like a cap. And then you flood that with liquid helium, and that's what keeps the quantum computer running. This particular quantum computer has 128 qubits, but it's still a work in process because you see it's not operational. It's not operational, and you can tell that because its outer casing has been removed. This may just be a demonstrator unit that they went, look, a quantum computer. So a couple of things you can take away from this picture. Quantum computers are huge for having such tiny qubits. They require liquid helium to maintain that temperature. They're obviously expensive to build with all that little intricate wiring. And you know, they're expensive to run because you have to have liquid helium, which means they're not going to replace your laptop, tablet, or mobile computer anytime soon. So just hang in there with the classical computers. Here's IBM's quantum computer. This one's a little more to scale. You see the picture on the left of the man and the woman standing next to the computer. It really is about 5 feet tall. And they jokingly refer to that as compact because it's smaller than the Google one. But a white chamber on the outside was very, just, you know, throw some paint on it, put some handles on it, kind of easy to build, but it wasn't very attractive. So then IBM changed the chamber on the outside of it to be this very shiny, chromy looking thing, which made it very much more attractive and oh so techie looking, but it's still 5 feet tall. It just has this little curve at the top to make the background scenery look interesting. For those people that remember the early days of supercomputers, Cray computers were circular in order to shorten up the distance of the wires between the circuits. And because it was circular, the power supply on the bottom was just a flat, giant metal enclosure. And so somebody had the idea, why don't we put bench seating on top of the power supply so you can, make it look like furniture. And I'm sure that they were made more attractive and, sold more Cray supercomputers because of that. And later on, they came out with a version of the Cray called Bubbles. And they actually used artificial human plasma as a cooling agent instead of water, because water is corrosive to electronics. And they used the artificial plasma to cool the heating of the computer to keep it from frying itself. And the way that they would cool down the plasma is they would blow air bubbles through it. So they would have these two glass plates that the plasma would be flowing through, and they would blow cold air bubbles from the air conditioning unit up through it. And so you'd have this, this window of bubbles. So they called the computer Bubbles. But it's how to take something that's a problem, like it's big, it's super cooled, it's ugly, and make it look like furniture or make it look like a fancy sculpture. And then you can sell more of them. So people will buy them for their appearance and not buy them for, their limitations. So how much does a quantum computer cost? Well, the estimate that IBM put into it was $1 billion to develop their first quantum computer. How much does it cost for an individual quantum computer? How much does it cost per qubit? They aren't telling. But they only have 20 of them, and they're not going to sell you one, but you can lease time on it. So these aren't going to replace your laptop any soon. And even if you had one, you couldn't afford to run it. The picture in the middle, the white chamber with all the electronics to the right of it, the core of the quantum computer is the big white chamber. All the rest of the electronics there and the rack that it's in, that's the stuff you need to actually make the quantum computer work. So remember back to that picture of the IBM 370 occupying a room full of electronics? This is better. This is only like half a room full of electronics. And for scale, you can see the picture there on the right, the people working on it. And you can see in order to keep any dirt off the inside of the quantum computer, they're all wearing gloves because your fingerprints are larger than the qubits, because qubits are subatomic particles. Okay, I'll stop at this point or pause. And if anybody has any questions so far as to what they might have seen that would otherwise counter some of the things that I might have said about either general purpose computers or quantum computers.
Takes me back to the old days.
Well, here's two phrases that you'll probably remember from the old days. One is the von Neumann architecture. They had a way of describing what was a computer and what wasn't a computer by its architecture. If you could execute a certain set of instructions and you had basically input, processing, or an arithmetic logic unit, output, and a place to store things, you would have an instruction-based computer that was considered von Neumann. But it had a bottleneck. The bottleneck was if all you had was one storage bus to interface to, then if you wanted to execute an instruction that just ran off the internal registers, you would have to wait for a memory request like storing data back or reading the next data. You had to wait for that to complete before you could go fetch your next instruction from memory. So they came up with this thing. There was a variant of it called a Harvard architecture. The folks that are smart, I got a Harvard degree, so Harvard architecture. No, it's not related to Harvard. But a Harvard architecture is one where instead of having one bus interface to your storage, you actually have at least two, one for your instructions and one for your data. So you could actually be storing what your last instruction did, the results of the last instruction, while you're fetching the instruction to execute the next thing. And if the instruction that you fetched was only using the internal registers and not using memory, you could actually overlap the storage of the previous result with the execution of the next instruction. until you had to access memory again. So that was it was a dramatic improvement in processing because you could overlap all these things. But they took that to the next level and they started putting in things called caches. When the processor gets to be so much faster than the memory access, you can start to predictively execute instructions where the computer internally might execute the instructions so fast that when you find out, nope, that's not what I want, I'm going to branch over here and do something else, you can literally afford to just throw away the result that you aren't going to use. And the other thing is, instead of just storing one memory location or fetching one memory location, like just the next instruction, you would do a batch fetch or a burst fetch, where you would say, I know I'm going to be executing instructions down that direction, so I'll just fetch, 8 instructions at a time. Or if I'm going to go read some long list of data, I'll fetch 8, blocks of data at the same time. So that when the fetch completed, you'd have access to not only the data you need now, but maybe the next data you'd need without having to go back to memory again. So these are things that general purpose classical computers have done over the years to make them so much faster. So we're not starting at square one. We've already got advancements in classic computers that the quantum computers may someday want to replicate, like overlapping things, doing predictions, but not yet because they don't have enough qubits. Here's another way of comparing computers. Some people may have heard of a guy named Alan Turing back during how do we break the German code during World War II. He was one of the guys at Bletchley Park that worked on the Turing machines. He was not treated well by society though. So he came up with this concept called a Turing machine. And he had a process by which you could describe something as either being a genuine Turing machine or not. And for something that is a Turing machine, they describe it as being Turing complete. And Turing complete is something that has a state and it reads data, it reads symbols from some form of input. It performs operations on them. It then produces an output, and then it can update its original state based upon that decision. So you have to have an input, processing, decision making, output, and update your state. And if you have that ability, then you have something called a Turing machine, and it's considered Turing complete. If you've ever heard of the HTML programming language that web pages are based upon, HTML as a programming language is not considered Turing complete because for security, it deliberately says, and you can't go back and change your own state. So if you were running an HTML page that said, I'm going to go execute these web page instructions, and then I'm going to adjust myself to now go off and do something malicious. Well, if you prevent it from ever going back and adjusting its original state, it can't do that algorithmically. So thankfully, HTML is not Turing complete, but that doesn't stop it from being something that processes data all the time. So because a Turing machine needs input and output directly, and a quantum computer relies upon a classical computer to do that for it, a quantum computer itself is not considered Turing complete. But once you add a classical computer to it, now it's Turing complete. So just a way of saying one of these things is not like the other, and one of them is better than the other. Classical computers are Turing complete. Quantum computers are going to get there eventually. Now we go back to that thing I referred to earlier as decoherence time. So in a classical computer, as long as I have electrical power and I set something to a 1 or a 0, it'll maintain that state. I don't have to worry about, and it'll kind of like drift away over time. As long as it has power, it'll remain whatever state I gave it for an indeterminate period of time. Well, it turns out qubits aren't like that. They will only maintain their current state for a limited amount of time before something comes in and destabilizes them. They'll basically just lose their state. I set it to a 1. It may be on its way to a 0, or it just became a 0. Well, that's its decoherence time. And there's 2 parameters that determine how long it will retain whatever value you set it to. One is the relaxation. In other words, it runs out of energy. And the other one is something called dephasing. Something comes in and disturbs it, and it loses its whatever phase you've set it to. But they don't know all the reasons why dephasing occurs. They know things like radio waves and stray electrons, and maybe it's something else that comes in and dephases it. But the dephasing is the shorter, the T2 parameter is the shorter one. The initial quantum computer design had a T2 of under 10 seconds. Imagine how usable a computer would be if you set a 1-bit to a 1-bit, and after 10 seconds, you had no idea what the state of the bit was. It's just not a 1. I set it to a 1 or a 0. It's just not that anymore. It's no longer deterministic as to what I set it to. So that made the initial quantum computers, which only had a few qubits, kind of unusable. But someday soon, current quantum computers have a T2 parameter of 10 minutes. How many algorithms can you run, no matter how fast the computer goes, where the total amount of time it takes to run it is 5 or 6 minutes? Because as you get close to 10 minutes, it destabilizes and you're not going to get the number you want. So although quantum computers can run really, really, really fast, how fast they need to run and be stable is based upon what algorithms you want to run on them. If the algorithm you want to run cycles for longer than the decoherence time of its qubits, you're not going to get an answer because the computer will fail before the algorithm ever completes. So it harkens back to the days of the Cray 1 supercomputers, which had a mean time between failure of about 50 hours because they would overheat, components would fry. So if you wanted to run an algorithm that took longer than 50 hours to come up with a conclusion, a Cray 1 supercomputer, despite spending millions on it and it running very, very fast, it could not run your algorithm because it just wouldn't last long enough. So I read recently that they're coming up with a new kind of quantum computer qubit that's based upon phosphorus 31, basically radioactive phosphorus electrons, the ions. And as long as you isotopically purify them in another form of material called silicon 28, at room temperature, you might be able to get your qubit to last as long as 39 minutes. All I can say is, golly gee, 39 minutes. Imagine spending that much money on a computer that you start running your program, and if your program takes longer than 39 minutes, might as well go back to square one because it's not going to come out with any answer. So when you look at quantum computers and they start talking about how wonderful they are, just ask them, what's your current decoherence time? What's the T2 parameter? And they'll start to, we're up to 40 minutes. Let me know when it comes out to be an indeterminate period of time, like classical computers. So how do you get information in and out? On classical computers, you have little electrically conductive things called traces that go into and out of the computer, and they send out the ones and the zeros. So they can do things like it's on, it's off, and they can tell the outside world that, or the outside world can send that in. Or you want to measure something, you can use analog to digital converters, or digital to analog converters, which are just a series of bits, ones and zeros, that tell you values. So you can do that because the inputs and outputs of a classical computer are electrically conductive, all those pins on the microprocessor are ways of getting not only power and ground, but data in and data out. You can't do that on a quantum computer, because if you're using electrons as your qubits and you introduce electrons to say 0 or 1 coming into the qubit, it'll actually destabilize the qubit. So what you use is microwaves. You essentially have an electron and you spit a photon at it to make it change state, or you get a photon out from it, which destabilizes the qubit, and now you can tell it's a 1 or a 0. So it's destructive in its reading. So to get data into and out of a quantum computer qubit, you need a little tiny coax cable going into one side of a qubit and coming out the other for every qubit. So this is heavy, but I did bold the appropriate numbers here. The size of a qubit is roughly the size of an electron. So it's 2.818 times 10 to the minus 15, very subatomic. Classical computers are now doing their lithography, their etching of the chips using UV, ultraviolet. So they can get it down to 1.35 times 10 to the minus 7. See, that's minus 7 versus minus 15. Okay, so although classical computer bits are very, very small, they are still huge compared to a qubit. However, since a qubit needs this little tiny coax cable coming in and going out to do the microwave sending and receiving, the coax cable determines how small the usable circuit is. Not the qubit itself, because that's an electron, but the getting data in, getting data out, that's 1 times 10 to the minus 4. And you can see that the minus 4 is gargantuan compared to the minus 7 of a bit in an integrated circuit. So they need to solve that problem. But classical computers are getting smaller too. They're going from using UV to using X-rays to etch the transistors. And when they do that, they're going to get down from 1.35 times 10 to the minus 7 down to 1 times 10 to the minus 8. So they're going to, shrink them down in half, which means you can now put 4 times as many transistors on the same size chip. But there are labs that are trying to get a transistor down to a single atom, which is still bigger than an electron, but much, much smaller. It's times 10 to the minus 10th. And they've actually done an experiment where a single silver atom could be represented as a transistor. So it would hold a 0-bit or a 1-bit. And the other thing to think about is how close you can put things together. In a classical computer, I can have the bits not only close together, but I can actually etch them in 3D. So I can actually make the transistors line up vertically. So I can actually stack them in 3D as I draw them on the chip. So I can have billions of transistors in something the size of a postage stamp. I can't do that with a quantum computer yet because all those little coaxes take up space. But since I'm working with radio waves in the microwave spectrum, I need to separate out all my qubits. If you remember that Google computer, you saw all the wires, those coax wires, and there must have been 3/4 to almost an inch separating them. That's as close as you can get the qubits together, is a good portion of an inch or many millimeters. Otherwise, the RF field, the microwaves of one qubit, will affect the adjoining qubits. You got to separate them out. So they need new physics to solve these kinds of problems. And by the way, that's the limit as to why you can only get to 1,000 qubits in a quantum computer core that's the size of a tree log. Helen often does the sizes and distances demonstration for the kids, so they get a feeling for relative size and distance of like the moon and the earth and separation between them. Here's the same sort of thing. We're talking about things like the size of an electron, these little tiny coaxes, and how far apart things need to be versus how far. Here's an analogy. So if you said, Let's scale a qubit up to the size of an ink spot on a piece of paper. Let's make an ink spot 1 millimeter in diameter. So that 1 millimeter represents my qubit size, which is 1 times 10 to the minus 15 meters. So I can see an ink spot, 1 millimeter diameter ink spot. How big would the coax cable be that would be connecting the input and output of my qubit? It would be about 2 meters in diameter. So my little 1 millimeter ink spot needs a coax that would be analogous to something 6 feet in diameter. That's one of those going in and one of those going out compared to the size of the qubit. So does a qubit need to be an electron? No, because the scale of it, it's just impractical. Also, if you wanted to separate apart your qubits to avoid them being RF interfered with, then, you know, separating them out in 3 dimensions by that ratio would be gargantuan. You would need a separation sphere around your millimeter sized qubit that would be 1 times 10 to the 12th times the size of the qubit. So huge. So until they solve these problems of how big is the thing you use to get data into and out, and how far apart do you have to have your qubits in order for them not to be interfering with one another, quantum computers are going to be this special niche market. But back in the day, classical computers had their limitations. In 1971, Intel came out with the first microprocessor. It was called a 4004 or a 4004. It had 2,250 transistors. It had 10 micron, not nanometer, but micrometer lithography. They could fit 280 bits worth of gates on the chip. The chip was about that big, the size of the end segment of your little finger. It had 16 internal registers, each of which was only 4 bits wide. It could access up to 4,096 bytes of memory, not megabytes, not gigabytes, but just bytes, and was clocked at a whopping 740,000 cycles per second, not gigahertz, not even megahertz, just kilohertz. It could run a whopping 92,500 instructions per second. And it took 10.8 microseconds to run an instruction. And because it was only 4 bits, if you wanted to add 2 8-digit numbers together, it would take 80 instructions, but it would run at room temperature. You didn't need any supercooling, and the chip sold for about $60. But that's what microprocessors were like 50 years ago. So let's give quantum computers about 50 years for their technology to mature, and we'll check back in. As I like to say, let's put a push pin in that and come back later. And more than a few years. So how do you scale it up? Well, classical computers have this thing called scalar, where they actually build an enormous integrated circuit. The integrated circuit itself is about 8 inches in diameter on a silicon disk, a silicon wafer. And they etch not just, you know, one microprocessor and then cut it loose and that's a microprocessor chip. They actually leave it all together and they cut hundreds of microprocessors and RAM and IO interfaces, and they put it all on one 8-inch diameter wafer. It's called superscalar. So instead of having a supercomputer where you had components that had to connect to each other with wires and cables, you just etched the whole thing on one giant chip. And they've actually made a supercomputer that had 1 trillion transistors on a single wafer. That's you know, a supercomputer on something the size of a dinner plate. And they're now starting to produce those as commercial products. Well, if you can make a supercomputer that size to have that many processors If it takes too long to run, spread it out. Let more processors run in parallel, because if you need it to run in parallel for your quantum computer, then you can certainly have it run in parallel on your classical computer. Not to be outdone, there is a company that is working to not superscalar quantum computers, but do multiple qubits on a single chip and call it system on a chip technology to link, small groups of qubits to make bigger ones. Okay, this is a lot of words, but if you wade through it, what you're going to find out is there's been competition for classical computer designs all along, and one that's been chasing it, and they've been switching roles and chasing each other for a long time, is complex instruction set computers versus reduced instruction set computers. At one point, RISC or RISC had the edge, but it consumed a lot of power. So the CISC, the complex computers, took some lessons from the design of the RISC computers and made themselves better, and then shrunk down the die further. And by making them clock faster and having chip caches, and well, the difference between RISC and CISC is down to about 20% difference. So at some point, you may find that classical computers are going to continue to improve, and quantum computers may not be able to improve fast enough to keep ahead of classical computers. So there may always be a difference between the two. If it gets to the point where classical computers are still getting cheaper, quantum computers are going to have to change what they're doing to make them anywhere near cheap enough to compete. Okay, here's clues. These are sort of corporate business computer kinds of clues. If very large companies like IBM and Google and Microsoft and such are spending billions to build a reasonably small qubit computer, let's say under 1,000 qubits, whereas classical computers are working on billions of transistors to come away with, trillion computer superscalars and terabytes of storage, at what point do they cross over? So if they can make a quantum computer really, really fast, and they can find really short algorithms to run on them, then it will be beneficial for other large corporations to buy time or to buy quantum computers, just like at one time when you had to do all your bookkeeping by hand, it was much cheaper in the long run to go lease an IBM 370 computer because it could do your accounting problems so much faster and more reliable. Well, quantum computers may fill that same sort of niche. If they can run certain very valuable algorithms very much faster than classical computers, to the point where there's a benefit of it, and that benefit produces a multi-million-dollar gain for large corporations, then large corporations will want to invest in quantum computers despite all of their shortcomings. This harkens back to the days of early supercomputers, where the revenue stream for the corporation making the supercomputer, like an IBM or a Fujitsu or a Hitachi or a Cray, was very nice. But the computers were replaced by smaller, cheaper, faster computers. They kind of had to get out of that business. Now, what they're doing is they're making supercomputers that are based upon inexpensive computer chips, just many tens of thousands of them. So they always have that edge. So a higher density, faster running supercomputer will always have its maximum number of processors edge. So that says it's still worth it to spend on supercomputers. Well, quantum computers may wind up displacing classical supercomputers and that edge. So, but architecturally, some of these problems never go away. Parallelism, how much parallelism, how fast is a particular component of the parallelism? there'll always be some math problem out there just waiting to be solved. But this time out, here's what the big boys are missing. So the likes of IBM, Google, Microsoft are putting billions into quantum computers. There are these things called Kickstarter companies where some people get together and go, hey, that looks interesting. I've got some, thousands of dollars to basically donate into accelerating that. And if that company ever goes public, I get a piece of the action. Well, Kickstarters are doing that, and they're funding quantum computer companies. So there are upstart, disruptor small companies that are getting into quantum computers, and the large corporations that have spent their billions may not be able to reap their thick revenues for as long as they think, because if there are fast advances in quantum computers, they may strip away that thick revenue before they can ever get all the money back out of them. Here's a disruptor. Remember me showing you the massive picture of the quantum computer and all the electronics it required? There is a disruptor group in China called Systech, or SpinQ. And here is a artist rendering of their supercomputer. It's going to have, maybe 64 to 128 qubits in it. But instead of it costing you $1 billion to have one, or instead of you renting time on one, for only the low price of $50,000, you can just go buy yourself one. This is their goal. But they also want to have, once they start making money off the $50,000 units, they want to take that money, reinvest it, and make it even smaller, faster, better, doing that shrink curve, which is the way things work in computing technology. They want to get it down to where you'd want to someday buy a $5,000 quantum computer add-on that might be a few hundred qubits. So at the point where a company like SpinQ starts selling $50,000 100 qubit quantum computers, what about that thick revenue that these big corporations want? Well, most likely a company will come along and offer SpinQ, $1 billion+ to make their product go away, absorb it, and then say, you still need to spend a lot of money on buying quantum computers. And then they'll come out with the next generation, and they'll have the $100,000 quantum computer that was the $50,000 one, that because they've absorbed the company, where are you going to go buy another one? Well, what about the software? Since the software for quantum computers needs to do these linear algebra algorithms, and you've got this strange way of getting the bits in and the bits out by microwaves, you need slightly different constructs in the programming language to do this. And they've actually come up with a couple of new programming languages in order to do this. The Python programming language, they've simply added a library to it and called it the QTIP library, Quantum Transaction Interface Processing, which I thought was magical. So QTIP is just, well, if you already know Python, this is just like adding a new library to it. But Microsoft actually came out with a whole new programming language. They've got C#. They came out with Q#. And IBM, in order to keep things proprietary where they can keep that nice thick revenue stream, they came out with a development library called Qiskit, Qiskit. So look forward to more of the software adapting itself in order to make quantum computers more usable for classical algorithms. Supercomputers had to go through the same thing. When they first came out with supercomputers that were asymmetrical, it was hard to map your Fortran programming algorithm onto them. They then came out with symmetrical multiprocessors where each of the processors was identical in its abilities, and therefore you could now just decompose your algorithm and give each one of the processors a piece of the action, and it could execute in parallel. So these programming languages are meant to take classical problems and allow them to be mapped onto quantum computers. So how you get the data in and out is still a problem. So once we have a lot of parallel qubits, how you get the data in and out to make it usable is still going to be a problem. So sometimes you solve problems, sometimes you create problems. Then again, quantum computers may be, you know, today's bubble memory. We may make classical computers so small that the need for all the effort and the cost of quantum computing kind of goes away. It may be, you know, similar to fusion power plants. It's always in the next decade, they'll be commercially viable, but not yet. But in the meantime, keep giving us research money until quantum computers, you know, break the 1,000 barrier and get to at least tens of millions of qubits per computer, and the computers are not room sized. They're going to have a niche marketplace. So put a push pin in quantum computers. We'll get back to it in a few years, just like fusion power. And if you want more marketing hype or some of the things that I've explained, you'd rather, you know, see a Intel marketing video on it, because they may explain it in a manner where you might understand it better. There's an Intel video for that. And you may hear discussions about AI learning computers or compute modules. And that's not quite the same as a quantum computer because they don't use quantum physics. However, the AI learning computers are fast enough that they're actually giving them quantum physics math problems to solve. An AI deep learning computer is nothing more than a lot of off-the-shelf high-speed computer parts, you know, microprocessors, graphical processing units that have hundreds to thousands of computing cores in them, and they can make desktop computers out of these that are roughly the same, you know, a couple of $1,000 price ballpark as a high-end gaming laptop. And they'll execute things very fast in parallel. So they're starting to rob some of the marketplace of supercomputers as just being desktop learning computers. But the terminology may be interwoven of quantum this and learning that and AI that, but just know that they're not really quantum computers. They're just really high density, very fast classical computers. Okay. And with that, now it's time for any questions, comments.
This is great stuff. We're looking into the future.
I knew it was going to be a deep topic. I'm going to edit it and put it out there, and let's just see if it draws any attention. Because remember, the Broward Astronomy YouTube page is open to the public, and when I post things out there, anybody that's subscribed to the YouTube page is going to see it. And when I post it on the YouTube page, I also post it on the Facebook page for Broward Astronomy. So if somebody is subscribed to either one of them, they'll see that, oh, look, we're talking about quantum computers. And if they can, you know, keep their head above water long enough to watch the entire video, then they may find it interesting, or they may want to ask other questions, or they may say, hey, we've got new technology that solves some of those problems you were talking about. I would be interested in looking at that. But I think we better give quantum computers at least another 10, 20 years before they start getting past the cusp of requiring liquid helium and having only, you know, 1,000 qubits.
Yeah, what about probability? I figure probability is much faster.
Well, that's the part that I was looking for some concrete explanation of. What is the value of having a probabilistic value in a qubit. Okay, I'm used to it's a 0 or it's a 1. It's deterministic. If I set it to a 1 and I come back, it's going to be a 1. This concept of I can try and set it to a 1 and it might maybe be a 1 or it might maybe be a 0 probabilistically. Okay, so if I have a large array and I want to do a linear math problem, I can just pump zeros into all my qubits and they will probabilistically, set themselves to zeros or ones. And if I connect them up just right, my linear algebra problem will self-solve itself as all the values flow to the other end. But I have to have a determinist. I have to say, how do I arrive at knowing that I have the answer? So I've got to have I guess in linear algebra, they call it a discriminant. I've got to have some way of saying, I have an answer. How do I know when I have an answer?
Or you have an answer that's close enough to get you where you want to go.
At one time we actually had that. How many people remember fuzzy logic?
Yep.
Yeah. Fuzzy logic was all the rage. You wanted to go buy your vacuum cleaner with fuzzy logic in it so it would vacuum better. Or you wanted to go buy your toaster with fuzzy logic in it so it would make your toast better. And it turns out fuzzy logic is just a way of saying random.
Yeah.
So if you have a computer that probabilistically has not a value you've set, but a value you tried to set that randomly may be a different value, I'm not quite sure what the value of it is algorithmically, or maybe my brain is just locked into classical computer designs and I know how to solve a problem. I do a compare and I do a branch. So if I want to see if this number is greater than that one, or if I'm sorting a string of characters and I want to see that this one's less than that one, I take two values and I do a compare and it either goes left or it goes right. And that's how computers work. But trying to put in a 0 and it may or may not be a 0 or a 1 on the other side.
It's kind of scary. Yeah.
And no, it's not scary. It's just,
Well, it depends
how
on
do I shape my classical computer software program, my goal that I'm trying to, how do I reshape that for this probabilistic determination? I want to know, is the light going to be green or is the light going to be red? I don't want to, well, the light may be green, it may be red. Now we've got another one in the middle called yellow. So if you were approaching a traffic signal and the traffic signal was either red, green, or maybe a little red, maybe a little green, would you know to stop at it or not?
You go real fast.
I don't know. So, I'm waiting for that answer. And in all of the research that I did, none of the marketing hype of any of these products would ever get down to that. How do you solve a determinant? Using something that's probabilistic. I don't know. But apparently there's enough demand for them that people are spending billions of dollars creating them and then maybe spending millions of dollars to buy time-sharing use of them. Or maybe even more millions to lease them. Okay, enough about quantum computers. It's actually almost 11:30. We have about 30 minutes before people turn into pumpkins. As I mentioned, next week, we're going to be talking about US commercial spaceports. And the following week, it won't be as dense and thick as this one was, but we'll be talking about how we just measure everything in electrons. And then the following week, we're going to talk about stellar explosions, novas, supernovas, hypernovas, and unnovas or false supernovas. And hopefully by then I'll get the camera installed and we'll show off I want to look at something in the sky. I'll have to evaluate what the moon phase and moon visibility is to know if the moon's going to be up in the correct part of the sky where we can at least try the camera on the moon. I know that the larger planets, the Jupiter and Saturn, they're up well after midnight at the moment. So probably won't be seeing them.